Welcome to RF Transceiver Design course. We have discussed up to now all the lectures. We try to understand the RF transceiver design components and how to design a RF transceivers. Now we will see entire system level picture, and if we want to design a transceiver, then how we can proceed. So if we want to design a transceiver, one of the important point is a link budget. So here link budget will help us to understand at what uh, level your loss is there, how much gain you are achieving, and what should be the receiver sensitivity, that all analysis can be done. So for that, in the slide there is a picture in which there is a on the left side there is a power, and at different place how this power is changing. So if you see that PTX, it is a transmitted power which is shown by the blue color. So this transmitted power will have some transmitted loss in the transmitter. There might be a different connectors, and that connectors will add the loss, and what will happen, that can be given by LTX. After that there will be the antenna, that is a transmitter antenna, and that has a gain. So your power level again will increase due to the gain of the antenna. Once that is radiating, so that power is called the EIRP, effective isotropic radiated power. So this radiated power will radiate in the air. Now once it will radiate in the air, it will have a path loss. So with different distance, it will, that signal will be attenuated, and it will come across different paths, and again it will come to the receiver antenna. So that uh, receiver antenna has a certain gain which will be added. So this green color will show the antenna gain. So after that, again there is a some connector or receiver connector losses, cables losses will be there, and it will receive the power which is a received, given by received power, and there is a sensitivity of receiver. We already have discussed the sensitivity of receiver. Now there should be a sufficient link margin, and we need to provide a certain margin when we try to design a receiver or transmitter. So by considering all this loss and gain, so from transmitter to receiver, when we account all loss and gain and powers, this entire method is called a link budget. So we need to have a link budget by considering the margin and analysis, that how you will distribute the power from transmitter to the receiver. And there is a receiver power PRX can be given by PTX, transmitted power, uh, minus LTX, that is a loss which is given by minus LTX, then plus CTX minus path loss plus GRX, again there is a loss in the Rx. So that is at receiver side. And for free space path loss, you can write it down 4 pi r by lambda whole square. So this is the equation of a free space path loss. There are different kind of path loss models also you can use to estimate that what kind of how much amount of power will be received to the receiver. There is a possibility that your either your transmitter or your receiver, mostly transmitter will be steady and receiver will be moving. So which is mobile in if one of the component means one of the transmitter or receiver, any one which is a mobile in nature, then wha- what will happen, that you also need to consider the change in the path loss, means amount of power change, and there is this link margin will also change. This method can be used in any system design, either you are designing a satellite system, or if you are designing a mobile system, if you are designing the local area networks. So in all the transmitter and receiver design, or for wireless communication front end, you need to have an idea of the link budget and the power and loss that it is adding. So based on that, once you know the power at each stage, you can, because you are going to design either transmitter or a receiver. So that once you know the parameter of the power and other parameters, you can start designing the receiver or transmitter. So when we are designing, when we are considering the system design, during the when we derive the transceiver performance parameter, we need to have a equal budget allocation for each component. Let us say LNA means noise figures, and linearity means how you can have a, you need to have a certain margin needs to be added. That sufficient margin will help to perform this entire RF front end reception more effective. And it should, while designing, we should also consider that both the transmitter and receiver is going to corrupt the signal. By accounting that, we can, by keeping the sufficient margin, if we design the transceiver, then it will work. So while designing the receiver, what are the parameters that we want, and we already have discussed, like a noise figure, that is, and a sensitivity, how much non-linearity, automatic gain control range, and maximum IQ mismatch, image rejections. So that all will be encountered in the non-linearity. And when we are designing the transmitter, the important parameter of the transmitter is the linearity, gain, IQ imbalance, and there is a possibility that efficiency also needs to be considered. Receiver and transmitter parameters, while when we understand about this parameter, we also needs to identify the receiver architecture. This is also very important. If you are designing the receiver for various application, how much sensitive your data is, and what are the configuration. We already have discussed the heterodyne, homodyne. Even when we discuss the mixer design, we have discussed reconfigurable receiver architectures. So what is the application that you are going to use, and based on that, you need to decide a receiver architecture. Once you know the receiver architecture, the frequency planning, so frequency planning, and the based on the frequency planning, you need to do design the frequency synthesizer. So all these means the four modules. One is the receiver parameters, transmitter parameter, receiver architecture, and transmitter architecture are more or less similar to receiver architecture. You also need to do the frequency planning and frequency synthesizer design. So once you do this, you can start designing individual component, and as discussed in initial lectures, you need to go through the all the design steps. So if we consider the receiver, first parameter that is important that you need to estimate, that is a noise figure. So the noise figure estimation, how can you estimate the noise figure for a certain application? So, we already have discussed the basic of communication and certain standards also. So, if you go to the standard document, there is a packet error rate or beat error rate will be provided. So, packet error rate, and based on packet error rate, beat error rate, or certain modulation scheme like QAM or BPSK or OFDM, inclusion of OFDM, that will provide the idea of the SNR. So, there is a standard definitions available based on the modulation scheme and beat error rate. You can estimate the SNR. So, once you have estimated the SNR, and if you know the bandwidth of your system or bandwidth of your signal, then you can estimate the uh, sensitivity. So, uh, sensitivity is also provided. Once you know the sensitivity, SNR, bandwidth, you can find the overall noise figure. How you can get the sensitivity? You can get the sensitivity by doing the link budget analysis that we already have discussed, that what is the amount of power level is going to come. So, if let us say for example, if you have a 30 dBm power which is transmitted, and there are a path loss of around 120 dB. If there is a path loss of 120 dB, then there is a minus 90 dBm signal is going to come at the receiver antenna, and that receiver antenna, let us say, because the normal mobile antenna does not have that much gain. So, it will have a 1 or 2 dB I gain, but that if we consider, or if we directly consider minus 90 dBm as a sensitivity which is coming to the receiver. And once you know the sensitivity, we already have equation of sensitivity which is a minus 174. So, sensitivity, as if we note it down as minus 174 dBm per hertz plus noise figure plus bandwidth plus SNR. This is a 10 log bandwidth, and SNR which is a, so you know the SNR, you know the bandwidth, you know the sensitivity, you can find out the noise figure. So, once you find out the noise figure of receiver, you need to add a sufficient margin of the loss. Let us say if there is a switch are used to do the frequency division duplexing or selecting the channel, that switch also needs to be, loss of the switch needs to be considered. If you have used a SAW filter, that filter loss also needs to be considered, and so that whatever noise figure that you achieved, then you need to have a sufficient margin for other losses. And you as I already told, that you also need to consider that your receiver is stationary or moving. Then you can also you require a variability in the gain as well. Then second important point is a nonlinearity. So, nonlinearity, how will you find the nonlinearity? Let us say modulation scheme. If you are going to design the going to use the OFDM signal, it's required a certain range of the, means its maxima and minima has certain range, and based on that range you can either 9 dB or 10 dB range, you can identify that you should have a that much 1 dB compression point, so that it can cover that entire full swing. It is also depend upon the blocker information, that what are the nonlinearity is also depend upon what are the kind of blockers which are going to come, or in band blockers, out of band blockers. This will and while discussing the low noise amplifier, we have tried to consider one example also. So based on that, this IAP3 or 1 dB compression can be identified. It depends upon peak to average power ratio for OFDM signals. So nonlinearity idea can also, the numbers for nonlinearity can also be calculated by using the all these parameters. It can also help us, we already discussed in the oscillator, that while discussing the oscillator phase noise, based on the interferer and the blocker level, you can also estimate the phase noise of your oscillator. So various parameters you need to list it out, and for each components that you are going to design and put into the uh, design criteria. Then AGC range, automatic gain control range. The receiver must have automatically control its gain if the received signal level varies considerably. So while discussing the receiver architecture, we already understood that three goals of the receiver design, and one of the goal is to have the variability in the gain. So that is also very much important while designing the moving target, moving receiver. So you also need, because if you are near to the base station or far from the base station, the power level that you are receiving will vary. So however, your ADC require a full scale range so that it can sufficiently convert the signal to the digital, and then you can do the baseband processing. And it also follows that the receiver gain must vary to accommodate the rate dependent sensitivity. Here the challenge is to realize this gain range while maintaining a noise figure. So you also need to maintain a noise figure, because if you vary the gain, how generally we vary by changing the load or tuning the load. But if you tune the load, what will happen, it will change the bandwidth, and based on that your noise figure, your gain will change, your noise figure will change. So that is also one challenge as a designer, is to realize this gain range while maintaining a noise figure. And the receiver gain range is also determined by a maximum allowable desired input level. So you also need to know that what is the maximum allowable input level at the receiver. So this is related to receiver. If you see the transmitter chain must be linear enough, because nowadays we are trying to achieve a high data rate and a complex modulation scheme like OFDM. And when you are doing that, your transmitter should, and whenever there is a amplitude is involved in the modulation scheme, we have discussed at various places uh, that required a sufficiently linear system. So your transmitter chain must be linear enough to deliver desired modulated signal to the antenna with acceptable distortion. So in order to quantify the tolerable nonlinearity, a transmitter or power amplifier model must be assumed and simulated with such a signal. So it is better that your transmitter can be simulated with the uh, entire signal or band pass signal which is generated, so that you will get the idea of the nonlinearity. And in order to achieve the high linearity, we can assign most of the gain to the last PA stage and minimize the output swing of the preceding stage. That will help to have a sufficient linearity at the output, because and your power amplifier should be sufficiently linear. And we have also discussed the multiple techniques of how can linearity be improved. That techniques can be incorporated in order to achieve the linearity. And if we can minimize the number of stages in the transmitter chain, because as we are increasing the number of stage, the nonlinearity also will be cascaded, and we already have done the cascaded nonlinearity analysis. However, the last stage is more important, that is a power amplifier, and that should be have a sufficient linearity, and there are various methods are useful to improve this linearity. Moreover, the gain of transmitter chain from the baseband to the antenna somewhat depends on the design details. For example, a baseband swing of 0.2 volt peak to peak requires a gain of 20 to reach an output swing of 4 volt peak to peak, which is equivalent to the 16 dBm. And it is desirable to employ a relatively large baseband swing so as to minimize the effect of DC offsets and hence the carrier feed through. But mixer nonlinearity also constrains this choice, and the IQ imbalance is also necessary in transmitter. IQ imbalance necessary in the TX is similar to that of the receiver. So, that also needs to be considered while designing the transmitter, and it require a calibration in the transmitter path as well. A carrier signal feed through is also another source of corruption in direct conversion transmitter that we already have discussed while we discussed the transmitter. And for if we take example as a 11 IEEE 11 AG system, feed through of around minus 40 dBc is achieved by mean of baseband offset cancellation. So, this is how the while designing the transmitter or a receiver, all these points if you consider, and if you first find out the each parameters of LNA mixer, uh, PLL frequency synthesizer, phase noise, VCO, frequency planning, then you can start designing the individual component, and that individual component uh, then you can club it and make a complete transmitter and receiver chain. Now, in RF transceiver design, there is a big role of EDA tools. So, there is a big role of EDA simulation design in RF transceiver design. So, this electronic design automation or EDA is a big market segment which consists of software, hardware and services with the collective goal of assisting in defining, planning, designing, implementing, verifying and subsequently manufacturing of a semiconductor device or chips. So, these all EDA electronic design automation tools are important for designing the any semiconductor chip, not only RF transceiver design, but it is used for all the chips. So, if we consider the if you want to manufacture these devices, the primary provider of this service are a semiconductor foundries or fabs. So, if we think about the foundry or fabs, this foundry what it will provide, it will do the multiple testing of the devices, and that device will be properly modeled, and with the support of the EDA tool, that foundry will provide a design kit. So, this is very highly complex and costly facilities which are owned and operated by a very large or vertical integrated semiconductor companies, or it is independent or pure play manufacturing service provider. So this, once you have a this PD case available and this EDA tool, you can use it and make a design. But while designing, you can always consider all the whatever we have studied, the basic understanding of the design, and then you can start your design in the EDA tool. Why is EDA important? Semiconductor chips are incredibly complex. And why it is complex? Because in all the analysis we have done, we have considered very basic models. But if we go for a complex model, why we are going for a complex models? Because we want to mimic the uh, measured result in the simulated result. How we can go closer to the measured result? If we can add a more non idealities in our design kit. If we add a more non ideality in our design kit, then we can easily go closer to the our measured result. But if we do not have a sufficient non ideality, then the getting the 100% yield or getting the maximum output whatever we desired is difficult. So state of art devices can contain over 1 billion circuits elements, and it is very difficult without the EDA tools. All of these elements can interact with each other in subtle ways, and variation in the manufacturing process can introduce a more subtle interaction and changes its behavior. There is a simply no way to manage the level of complexity without the sophisticated automation. So here means if you want to also explore, AI is also going to come into the picture. So artificial intelligence, with the use of EDA, you can reproduce, you can refine your design by using this all the EDA softwares. So nowadays there is a possibility of integrating the AI into the EDA tools to design the RF transceiver design. So that can also be one of the area where many companies and EDA tool designer companies are approaching, and RF is critical in that, because you need to consider electromagnetic effect, you need to consider the circuit design effect, and all uh, combined in the design. Even analog circuits, mixed signal circuits and RF, these all are combined in the RF transceiver design. So this critical technology, without it, it would be impossible to design and manufacture today's semiconductor devices, and chips error cannot be patched, because the fabrication process is a complex and costly. So the entire chip must be redesigned and remanufactured. The time and cost of this process are often too long and too expensive, resulting in a failure of this entire project. So without EDA tools, these challenges cannot be met. There are various companies like Synopsys, Cadence, Mentor Graphics are primary companies leading in this space. There are some EDA tools, Keysight ADS or LT Spice. Some of the free open source softwares are also available and emerging, which will help to design the complex chip like a RF transceiver design. Some of only few has been listed. There are many more tools will be available. How these EDA tools work? It is very sophisticated and a complex software program that function primarily in one or three ways to assist with the design and manufacturing of the chips: simulation, design tools and a verification tools. So, in simulation took tools take a description of the proposed circuit and predict its behavior before it is implemented. In design tools, take a description of the proposed circuit function and assemble the collection of circuits element that implement that function. So, we need to implement that function, and this is a logical process. Assemble and connect the circuit element and a physical process create the interconnected geometry shapes that will implement the circuit during the manufacturing. There is a verification tools. So, that you can verify means the whatever you have designed with the actual, which examining the chip logically or physical representation to determine if it is a if the resultant design is a connected correctly and will deliver the required performance. So, these are the simulation design types of EDA tools, uh, and even system design tools are available. So, in simulation tools take description of proposed circuit and predict the behavior before it is implemented. This is typically presented in a standard hardware description language such as Verilog or VHDL. Simulation tools perform a various operation to predict the resultant behavior of the circuit, and design tools take a description of a proposed circuit function. So, what are the description means you need a linearity, noise figure, all these are input, assemble the collection of the circuits element and implement that function. You also need to do logic synthesis. It can also be physical, also be a physical process where the geometry shapes that implement the circuit in the silicon are assembled, placed and routed together, and broadly this process known as a place and route. So, this is mostly used in digital, but in analog manually you need to do place and routing, and it can also take the form of an interactive process guide by a designer, which is a layout. Once layout is done, you need to do the layout and schematic verification, that is called layout versus schematic, and this is an iterative process. You need to start with change the design, you need to go to the simulation. So, this is how the EDA tools work. So, starting from the design to the chip fabrication means identifying this parameters, circuit parameters, then going through the design, and after that verifying the design through EDA tools. That EDA tool verification, it will reach to the layout and layout to schematic verification. There is a possibility that you need to use the multiple tools while designing the RF circuits, because if you are designing at very high frequency like sub terahertz or high frequency design, then it is difficult to incorporate all the methods in the single tool. So, some of the tools are good in EM analysis, some of the tools are good in circuit design. So, you need to merge and find out the uh, breach, means you need to bridge the gap between this and come out with the uh, final results, which should be comparable to the measured result. So, this is how you can use the multiple tools to make your RF transceiver design at very high frequency. So, once we have done the design, then the important part is RF transceiver testing. So, this RF transceiver testing is there are basically three ways of testing the chip. One is you can use the bond wire. So, this required RF testing. RF testing is also very much important in the complete design. We will go through the RF testing in the next class. However, I will brief you, this is a additional class. I will brief you about the RF transceiver testing and what are the ways we can test in the additional lectures. Thank you.